Welcome to EDU World Space.
We can treat this question using the superposition principle of electrodynamics, according to which a cylinder with a hole is the same as a cylinder with no hole plus a smaller cylinder with opposite charge density that will represent the hole. Then, in this situation, it is easier to treat the problem because of the following. The electric field E is then equals to E1 plus E2, where E1 is the electric field in the region of the hole in this situation, and E2 is the electric field here in the region of the hole in the second situation. We begin by calculating the electric field in situation number 1. In this situation, we will use Gauss's law. So the flux of electric field is given by the integral of the element of surface times the electric field. As you can see, an element of surface of a cylinder would be something like this. So this would be the vector dA. At the same time, we have a symmetry because the cylinder has a radial symmetry around its axis. So it produces an electric field that is also radial. So the electric field produced also points in the radial directions. Therefore, dA is parallel to E, and this means that this inner product is given by the integral then of the magnitude of dA times the magnitude of E. The magnitude of the electric field do not depend on the area of the Gaussian. Then we can write it as E times the integral of dA. Then the flux of electric field through the Gaussian is given by the magnitude of the electric field times the area of that Gaussian surface. At the same time, this is equal to the enclosed charge by the Gaussian surface divided by epsilon 0. Then, the electric field is given by the enclosed charge divided by the area of the Gaussian surface times epsilon 0. For the Gaussian surface, we have to choose something like this. A cylinder of radius small r, just like that. And that radius small r is such that it falls inside this region. As you can see, the Gaussian in this situation is also a cylinder, and the area of a cylinder is very simple to calculate. So the area of a cylinder is equals to 2 pi times r times L, where L is this measurement. Therefore, we conclude that E is equals to Q divided by 2 pi r L epsilon 0. And now we have to calculate what is the enclosed charge. To calculate the enclosed charge, we can use the charge density, because the enclosed charge is equal to the charge density times the volume of that Gaussian. The volume of a cylinder is very simple to calculate. It is just pi r squared times L, which is the area times the height. Then, using this expression, we get that this is equals to rho times pi times r squared times L divided by 2 pi r times L times epsilon 0. Now we can simplify whatever we can, so pi with pi, r with r, L with L, and we are left with an electric field that has a magnitude given by rho times r divided by 2 times epsilon 0. Notice that it doesn't depend on L. And then, given the situation, it's very simple to write it in vector notation. So the vector E is equals to rho divided by 2 epsilon 0 times vector r. So the electric field is parallel to the radial direction, as I said. Then, this is our E number 1. Now let me organize my board to calculate E number 2. For the second situation, we can use again the equation that we had just derived. So E2 is given by minus rho divided by 2 epsilon 0 times r, where r is a vector that points in the radial direction of the red cylinder, like this. Then you have to notice that this vector r is in this reference frame. In the reference frame y prime x. All we have to do now is move this vector r to to the other reference frame, yx. In order to do that, we just have to subtract from r this distance b, as if it was a vector. So we have to pick this reference frame and bring it to the left by b, like this. So all we have to do is subtract b from r. Then, performing this change of reference frame results in E2 given by minus rho divided by epsilon 0 times 2 times r minus b. Then we can finally use this expression and discover what is the electric field inside the hole. So E is given by rho times r divided by 2 epsilon 0 minus rho divided by 2 epsilon 0 times r. I'm using the distributive property of multiplication, plus r divided by 2 epsilon 0 times b. Then you can see that there is a cancellation of these two terms, and we end up with E given by rho divided by 2 epsilon 0 times b. So this is the electric field inside the hole.